Chapter 7, we saw that a nucleophile can replace a leaving group on a substrate in a single step by a bimolecular nucleophilic substrate reaction. Unimolecular nucleophile substrate consists of two steps. First, the leaving group leaves in the heterolytic step using a carbon cation intermediate, and there is a nucleophilic Then a nucleophilic attacks the carbon cation in coordinate steps. This one right here. So you have the lone pairs and the SN21 go from here to there to that carbon, from that carbon to the nucleophiles, and then you have two different groups. And this one, you have the carbon goes to that one, and then you have an intermediate right here, then you have your thing, and then you have your final product. A species is an overall reaction or overall product if it appears in the overall net reaction. A species and an intermediate if it does not appear in an overall reaction. This is the unimolecular elimination reaction. In Chapter 7, we saw a leaving group and a proton are eliminated from adjacent carbon atoms in a bimolecular reaction resulting in an additional pi bond. You have your base, lone pairs go to the hydrogen, you have your substrate over here, and then you have your overall reaction, and you have your overall products. And E1 also takes place in two steps. The first step, like the SN1 reaction, you have the intermediates and you have your bases, but you also have a coordinate step and SN1 mechanism.
How do we know that the mechanisms we have presented are correct? You observe the carbocation that serves as an intermediate, but because carbocation is very reactive and has a short life, it is very difficult to study the intermediate, which serves as the evidence to know if the mechanisms is right. So now we're going to talk about the rate of reaction. The rate of an SN2 reaction is directly proportional to the concentration of the nucleophile. That means as the concentration of the nucleophile increases, the rate of an SN2 reaction increases. The rate of an SN1 reaction is not dependent on the concentration, which means whatever the concentration of the nucleophile is, the concentration of the SN1 reaction is not going to change.
As far as rate laws go, in an E2 reaction, the rate is directly proportional to the concentration of the base. So if the concentration of the base increases, then the rate increases. And that is why the base is in the rate law. But when you get to an E1 mechanism, the rate is independent of the concentration of the base. So it basically doesn't matter how much base there is. It only matters how fast or slow the first step occurs. So here, the base is not even in the rate law. It would be in the second step, but that's irrelevant if the first step happens slow or doesn't happen at all. So what we need to know from this section is that the K constant decreases as delta G increases. So therefore, the reaction rate increases. Basically what that means is, initially, the energy has to get all the way from here to way up here. But in the second step, it only has to go from here to here. So that's just saying that the first step is the slower step and therefore the rate determining step. And then also, the K constant increases as temperature increases. So the reaction rate would increase as well.
Stereochemistry of an SN1 reaction. So if a tetrahedral stereocenter is formed in a single elementary step from an atom that is not a stereocenter, then both R and S configurations will be produced. As in this example, right here, the leaving group, which is chlorine, which is way up there, when it is removed, the top carbon on this carbocation becomes planar again rather than going back into the board. This allows the iodine to come in and either form the S configuration or the R configuration. Okay, so now we're going to talk about SN2 reactions and why they are so stereospecific. In the last part when we talked about SN1 reactions, we found out that both R and S configurations can be produced. However, in SN2 reactions, depending on the configuration of the original substrate, only the R or the S can be produced. Okay, so let's look at an example. In this molecule, here's our substrate, and here's our nucleophile. The nucleophile comes up and attacks the central carbon, the alpha carbon, from the opposite side of the leaving group. This is due to steric hindrance and charge repulsion. In addition to this happening, so the iodine coming in and the chlorine leaving, something called the Walden inversion occurs. This is essentially just a flipping of the molecule. In the book, they discussed the similarity to an umbrella when you're carrying it in a windstorm and it flips out. Okay, so the iodine comes in from the back, the chlorine leaves, we have the intermediate, and here is our final. Talk about the stereochemistry of an E2 reaction. An E2 reaction, just as a reminder, is a bimolecular elimination reaction, meaning that we have two molecules involved. We have our leaving group, our nucleophile, and our substrate. So our leaving group, in this case bromine, it leaves. We have this lone pair over here that really wants this hydrogen, so it comes over and bonds to this hydrogen, but we have these electrons over here now that are like, what do we do? And so it goes and forms a double bond right here, giving us this product. In the E1 reaction, we had the opportunity to have conformational isomers because we had that step that had the single bond, which, as we know, single bonds can rotate, but here we don't have that step. So the stereochemistry of an E2 reaction is stereospecific. So we start off here with 1s2r, and then we end up with E. So, but both of these you can see is pretty much trans. Okay, so something that is good to know is that E2 reactions are favored by the substrate conformation, in which the leaving group and the hydrogen atom that are eliminated are anti to each other. Okay, so now we're going to talk about the stereochemistry of an E1 reaction. Just a reminder of what an E1 reaction consists of: we have our substrate and the leaving group, and the first step of this reaction is for this leaving group to hit the road. So it leaves a carbocation, and we have our nucleophile that comes in and attacks the hydrogen, and thus leaves these bonds, or these electrons, to form a double bond and give you the products. But now we're going to talk about why this diagram is so complex. If it just does that, then why do we have such different products? Because of right here. During the step that has the carbocation, we have a single bond here, and we know that single bonds can rotate, thus giving us different conformational isomers. However, we know that steric strain is a bad thing, so steric strain, when it is in the Z conformation, as it is right here, is much less favorable than the E conformation, which is right here.
The first thing to remember when you're determining the reasonableness of a mechanism is that strong acids can't occur in basic conditions and strong bases can't occur in acidic conditions. So here in this mechanism we have basic conditions with the OH group, and then an SN2 reaction, and then a proton transfer reaction. But here we have a strong acid forming, and a strong acid is incompatible with basic conditions. So this mechanism does not work. This one, however, OH acting as a strong base comes in and takes away the hydrogen, and we never have the strong acid form over here. So in the order of proton transfer and then SN2, this reaction works and is reasonable because no strong acids form. So rule number 2 is that intermolecular proton transfer reactions are unreasonable. Here, the protons are being transferred within the same molecule, so that doesn't work. But here, water is assisting the transfer, and it's called a solvent-mediated proton transfer. So this oxygen takes away the protons, causing the electrons to go to OH, which in turn takes away this hydrogen, causing these electrons to go to nitrogen. So here water is assisting in the proton transfer reaction, causing water to be formed and the final product. The third rule that we need to remember is that termomolecular steps and other steps with higher molecularity are unreasonable. So basically the premise of this is that if there's 3 molecules, all of these steps can't occur at the same time, and that is the definition of an elementary step, that it occurs as a single event. So termomolecular and those with higher molecularity are very unlikely to happen. When it comes to carbocation rearrangements, we talked about this in chapter 7, and this chapter basically introduced us to the fact that carbocation rearrangements can occur with other steps. So here, heterolysis occurs, and then we see that the positive charge would actually be better accommodated on this tertiary carbon rather than this secondary carbon because it's more stable there. And so then that hydride shifts, and then you have coordination and proton transfer occur, resulting in a final product.
In chapter 8, we learned about curved arrow notation for SN1 mechanisms, curved arrow notation for E1 mechanisms, how to distinguish our own reactants and products from intermediates, free energy diagrams for SN1 and E1 mechanisms, and the rate laws of SN2, SN1, and E2 and E1, stereoselectivity of SN2, SN1, and E2 and E1, reasonableness of mechanisms, and carbocation rearrangement.